So yeah, let's get started. So welcome back to this course. So we covered a very brief and a very high-level overview last lecture of the course. And this time we're going to start with an introduction to deep learning. So this is the first part. This is going to be two parts. So the lecture next week is also the second part of this introduction. So before we get into the deep learning, I want to recap what we did last lecture. So what we talked about were three really important general tasks in science that we want to solve. And I encourage you to think in an abstract way. So even though I'm showing kind of specific domains here, like engineering and medical imaging, these just apply to many different domains and they're kind of general concepts. And so the first concept is simulation. Starting from some input conditions of the system that we want to study, we want to simulate some outputs. Inverse problems is trying to do the reverse. It's typically a lot harder to do that, especially if the problem is very ill-posed. And then the kind of final big task is trying to understand the underlying physics or the laws that govern that system. And so that's kind of equation discovery. And I hopefully convinced you that, well, these are really important tasks, firstly, and also they have some really difficult challenges to solve. And machine learning can help across across different domains and across these tasks. And so then I told you about the field of scientific machine learning, and the whole point of this field is deep learning is really powerful, but we know it has a lot of flaws. So things like generalization and lack of interpretability. And so this is a new field that's come about, and the whole idea is to use the advantage that we have in science of all of our prior understanding and to really try and put that into the machine learning algorithm and blend the two to produce more powerful techniques. And so there's a whole plethora of techniques, and I started to introduce a few of them. And obviously we're going to talk about these way more in the course to come. And yeah, how do you put scientific principles into machine learning? I showed you that there were kind of three different kind of broad areas that you can do it. One is through your loss function, another is through the architecture, and a more complicated one maybe is these hybrid approaches where you take your existing algorithms for doing scientific tasks and you put machine learning into it in a very kind of blended way. Okay, so that's the recap. Let's start to learn about deep learning. So this is a slide I showed in the first lecture as well. I just want to recap. Deep learning has really taken the world by storm over the last decade. And as I said before, it's now in our everyday lives and permeates our lives today. So for example, when you carry out translation and autonomous driving is relying heavily on machine learning. And why now? Again, this is a slide I showed in the first lecture. Well, neural networks, the ideas of neural networks came from the 1950s, but there's these kind of three big reasons why deep learning is really popular today, and that's the rapidly increasing amounts of data that we have, the improvements in the hardware and the computing speed, especially the advent of kind of GPU computing for deep learning. And then the rich kind of ecosystem that's been developed, so PyTorch, TensorFlow, all these amazing deep learning packages that make it really easy to do deep learning in a few lines of code. Okay, so I mentioned this is part one of 2 lectures, and so my goal for you by the end of these 2 lectures is to understand how ChatGPT, this model that's super popular right now at predicting text and answering questions. My goal is for you to understand in more detail how this model actually works, how we train it, what the model actually, the architecture of the model looks like, and the data that we use to train it. Okay, and here's the course timeline. So as I said, we've already had the first course introduction. We're now on the second lecture, and hopefully you went along to the tutorial last week and had an introduction to PyTorch, one of the popular deep learning libraries there is today. Okay, so I've got kind of 4 main parts to this lecture. We might, if we get to the last part, that would be great. If we don't, that's okay too. The first part is giving you a very high-level idea of what deep learning is. We're going to introduce to you the core building block of deep learning, which are perceptrons. Then we're going to talk about the type of tasks that we use in kind of more pure computer science, the kind of tasks that deep learning is used for. So these things like supervised learning, unsupervised learning, classification, regression. And then we're going to go into more detail about how we actually train these neural networks and the algorithms that we use to efficiently train these models, which have millions and even billions of parameters. And so that's not actually a trivial thing to be able to train a network. Yeah, and if we get to it, I'm going to try and do some live coding for you. So I'm going to pull up some code and show you how easy it is to code a simple neural network in Python. And we're not even going to use any of the deep learning libraries. We're just going to try and use NumPy, which is just a basic array manipulation library. Okay, so before I talk about deep learning, it's really important to see this in the perspective of the field of artificial intelligence. And AI, machine learning, deep learning, these are terms that are thrown around a lot, not just in academia, but in industry too. And so, it can be very confusing to kind of separate what each term means. So this is the way that I like to think of it. I would say that artificial intelligence is a much broader field than machine learning and deep learning. And the kind of goal of AI is to produce kind of intelligent systems that mimic human behavior in some way. So learning about the world is one part of AI, but it's not everything. If you already know things, maybe you want to infer things from them. Maybe you want to plan a route to the airport, or you want to derive some math equation or something based on your prior knowledge. Machine learning at the moment is about learning the rules of the world rather than kind of searching through them or doing inference on them. So artificial intelligence has way more kind of areas. So like reasoning, for example, theorem proving, planning and search. These are really fundamental things that is really important to understand if you want to get into AI in general. Yeah, then you go down to machine learning, and this is about trying to figure out the patterns of the world and learning rules about the world. And what's important is deep learning is a subset of machine learning. So it's just one way of doing this kind of pattern extraction of the world. There are many other approaches, and you probably know of these already. So you have things like principal component analysis, support vector machines, Gaussian processes, and kind of Bayesian inference in general. These are all kind of types of machine learning. And then finally, you have deep learning, and this is about using neural networks specifically to extract patterns and learn about the world. And so then within deep learning, we have this whole zoo of different deep learning models. And so again, you've probably heard of these before. So MLPs, ResNets, diffusion models, GANs, transformers, etc. And so I'm going to try and give you, these two lectures are just focusing on the deep learning part. And I really recommend, if you want to get into machine learning and AI, to really move away from that as well and learn about these other fields. They're very important. Okay, so what is a neural network? As I said in the first lecture, a neural network is simply a flexible function that is fit to data. And if there's one thing that I want you to take away from this lecture is this idea, that there are so many neural networks out there, and they look very complicated, and they are in some ways. Their architecture is very complicated. If you look at a transformer or like a ResNet, for example, but every neural network practically can be thought of as doing this, where we have some training data here, and we just want to fit a curve to that data. And what I've shown here is just a one-dimensional example, but neural networks can be applied to inputs and outputs that are many more dimensions. So in general, neural networks learn a vector-valued function, where the input to the network is a vector and the output is a vector. If you think about neural networks that are trained to classify images, well, is an image a vector? It can be a vector if you flatten it. For example, you just take all the elements and turn it into a single vector. So you can pretty much always describe a learning task as learning a vector-valued function. And the neural network is great because as well as taking x as input, it also has these free parameters, which I'm calling theta here. And so the way the network learns is we just tune those parameters to fit the training data that we have. So this is the goal. Given our training data, find that function or find the values of the parameters theta, which let that function be as close as possible to the true function that we're trying to estimate. Okay, so we already hopefully know about function fitting. This is something I would hope many people have done before, fitting a line to some data, right? This is like basic statistics. And so if I told you that this data that I'm showing you is just data sampled from a polynomial, and maybe we've added a little bit of Gaussian noise to make it a bit of noise on the data too. So how would we fit a polynomial to this data? So we can just start with this function here. We say, okay, our approximation of the true function here, y hat, is just a polynomial. And the thing is, we don't know what the weights or the constant values of this polynomial are. And we want to try and learn them. So to do this is standard approach in statistics. Is we use a least squares approach. So we say we want the squared difference between our model, which is this polynomial, and the true data points. So these noisy Gaussian noisy points on the polynomial. We want the squared difference across all the summed across all the examples to be minimized. Ideally 0, but I mean, if there's noise on the data, then a polynomial is never going to get a loss which is 0. So we call this thing here, we call this the loss function in machine learning terminology. And the goal is just to find a value of theta that minimizes this loss function. So in this case, we can actually rewrite this whole thing using linear algebra. So you might think, oh, this is not actually linear. It's a polynomial. But actually, if you look at this long enough and you say, you can see that this model is actually linear if you take x and x squared and x cubed as your inputs rather than x itself. So you can just phrase it as a matrix here. So this matrix just contains all of our examples. This is example 1, example 2 as rows. And we just input x, x squared, x cubed. We also add 1 here. This is just to make sure that we can include this, what we would call a bias or the constant of the polynomial. And then we just times it by our values of theta here. And so as a matrix equation, y is phi times theta. And so then the problem, the minimization problem becomes the minimization of the L2 norm of this expression. And so because we know that this is a linear equation, we can actually solve it analytically. And it's easy enough to show that the optimal values of theta star here is this expression at the bottom. And so if you plug these values of theta star into the equation and plot them, then you can see you get a really nice fit to the training data. And it basically learns the same as the exact function that I was using to generate that data. Cool. So how are neural networks different? Well, actually, they're incredibly similar. Now what we have with a neural network is, again, an approximate function. And it's described by a neural network as a function of x. I'll go into what exactly NN is in a minute. And we use exactly the same approach. So we say, okay, we want to minimize the difference between the neural network's prediction and the training data that we have. And we can just use a least squares error. And we have this the same kind of optimization problem as we had before. So I guess the key difference here is because neural network is just in general an arbitrary function, we can't rewrite this in kind of linear algebra, or in general, we don't have an analytical solution. And so what we have to use is some type of optimization algorithm. We have to basically search over the values of theta to fit the neural network to the training data. And what is done for the vast majority of cases is we use gradient descent as our optimization algorithm. And so what we do is we take the gradient of this loss function with respect to the parameters of the neural network theta. And we do gradient descent steps to update our values of theta, and we do this many thousands of times, gradually stepping in the parameter space towards where we hope is a minima of the loss function. So we call this the loss function here. Okay, so then what exactly is neural network of X, right? And so this just depends on the specific neural network architecture that you choose. And so, as I said before, there are many different architectures. We have multi-layer perceptrons, convolutional neural networks, ResNets, transformers, etc., etc. But it's important to note these are all trained in the similar way: gradient descent and the loss function. So let's introduce our the most basic architecture, and this is called the multi-layer perceptron, also known as a fully connected network, a dense layer. There are different names for it in the different deep learning packages. So how do we actually define this function? So it's actually very simple. We take X, and remember X here is a vector in general, and we times that by a weight matrix, W. So this is just a 2D matrix. Add it to a bias vector, and then we pass it through what we call an activation function. So this just doesn't, it's just an element-wise function on each of the individual elements of that resulting matrix. And that's a basic layer in our multi-layer perceptron. And then we can just compose these layers together, and we can add as many as we want. So for example, if we do 2 layers, then we do the same procedure again. We times it by a weight matrix, add a bias vector. And for now, I haven't added another activation for the last layer of the network, but you can if you want. And so that really is it as a mathematical expression. This is what the function is. So then you ask kind of, well, why did we choose that? And I think this is the kind of mind shift that you have to take with machine learning. Traditionally, when we fit functions to data, we have a really good reason why we chose that form of the function. So for example, polynomial regression, we chose a polynomial and we fit the constants that we knew. But it's not immediately clear why you would choose this kind of multi-layer perceptron architecture to learn machine learning tasks. And so one kind of reason why we might choose it is basically, or the reason why people started looking into neural networks is from their biological inspiration. It's like, how does the brain work? How does it learn? Now, I want to give a really big caveat here that neural networks used in machine learning nowhere near close to the network that our brains, and it's only a very loose inspiration, I would say. But if you do look at a neuron, you can see it has kind of inputs, outputs, does some processing. It's kind of the same as what an individual neuron in one of these multi-layer perceptrons does. So we can draw an MLP like this, and we can extract a single neuron from it. And what that neuron does is it takes its inputs here, and it has multiple inputs from the layer before. We times them by these weight values. We sum them together. We add a bias value, and then we pass that single value through an activation function. So this is what the expression looks like. So this is what happens just for a single neuron. And then when you do all of these neurons in parallel for each layer, we can just turn that into that matrix equation that I showed you before. So if I want to compute the output of these 2 end neurons in the last layer, it's just this weight matrix here times by the activations from the previous layer, added with the bias vectors. And we get exactly that equation that I showed in the slide before. So we also call these fully connected networks. And so the point is here that each neuron here is fully connected to each of the other neurons in the previous layers. So that's why they're called fully connected. Another interesting thing you should understand is the dimensionality of each layer. So suppose, for example, we start with X. X is like a 3-dimensional vector. We can actually choose in the hidden layers to expand that into a higher dimensional vector, say 5 elements of the vector in the middle layer. And then we can reduce that again to 2. And we're free to choose however many hidden units, we call them, in each of the layers. And that's kind of like a design choice when you're designing a neural network. You can choose these freely. And ultimately, those number of units just tells you what the shape of these weight and bias vectors are. Okay, so I said an activation function. So what do we actually use as those activations? And so the most common activation function today is a ReLU activation. And so this is a rectified linear unit. And the mathematical equation is just the max of 0 and x. So you can see when x is negative, we just get a 0 value. And then when x is positive, it's just y equals x. That's very popular. There are also many other activation functions that you can choose, and they've kind of come and gone in popularity through the history of machine learning. So one that we use quite a lot in scientific computing is this tanh x activation function. And what's good about the tanh function is that it's differentiable everywhere. You can see here we've got a discontinuity in the gradient at 0. So if we want functions, and we'll come on to this later when we talk about applying machine learning to scientific problems, if we want to learn functions that are continuous and differentiable, then we have to change the activation to make sure that the output of the network is also has that constraint. Okay, so now we can train a neural network using this function instead of a polynomial function in our optimization algorithm. And so this is a neural network training, and I set the neural network up to have 3 layers, so 2 hidden layers and 1 output layer. And you can see I'm learning a 1D function, so x is a single value, y is a single value. But in the middle, I've expanded x into 1, 2, 3, 4, 5, 6, 7, 8 element vector. So each hidden layer has 8 units. And I'm training this using that least squares loss function that I said before, and gradient descent. And yeah, you can see it takes maybe 2,000 training steps for the neural network to train. And there's a lot of really interesting things going on here. I mean, the first is, what does a neural network function start off as? And you can see it starts off as kind of a fairly straight line, and then eventually fits to the training data. What I also plotted here, I think is really cool to see, is how the weights of the network actually change as a function of the training step. So as the network's training, the width of the line here shows you is proportional to the strength of the weight, the value of the weight itself. And so what you can see is, yeah, these weights are changing, and some of them are very strong, and some of them are just kind of go very close to 0, and they're basically not used. And so you can kind of see this as the connections forming inside of the neural network. And I think this is really interesting to see. There's no kind of structure to these weights. They seem fairly random. And this is really important. Neural networks tend to learn like distributed representations of your inputs. So your input is kind of distributed across all those nodes and then formed back together when you get the output. And this is actually one of the core reasons why it's really hard to interpret what's going on in a neural network, because our features or inputs are kind of distributed across the network, especially if we're using fully connected networks. If we start to use CNNs, and I'll talk about them in a minute, we can see that they actually learn kind of important features about the world. Okay, so it kind of begs the question, like if I'm trying to fit a simple function, why should we even use neural networks? Well, yeah, sure. If you're doing polynomial regression, it's much better to use a polynomial if you know that's the case. But if we want to learn really complicated functions, neural networks are really powerful because they have this property called universal approximation. And this is the property that, with enough parameters, neural networks can approximate any complex function. And this is a really powerful statement. So I'm not giving this statement in a mathematically precise way, but this is an actual mathematical theorem, and it essentially says this, that if you choose a fully connected neural network with enough parameters in it, it can approximate any function. So we can learn any really, really complicated functions. For example, this is a function saying we have an image as an input to our network, and we want to output a classification of that image, so whether it's a dog, for example. This is just a function, right? This is x is like a matrix which can be turned into a vector, and y is a single value. So it's just a scalar function of a vector input. And neural networks turn out to be really great for doing these types of tasks. Now, the key thing inside of that multi-layer perceptron that makes it able to approximate any function is the activation function. So if I go back to the equation of the neural network here, so think about what would happen if you took away this activation function here. You would basically end up with a bunch of matrix multiplies and additions. And it's fairly easy to see that you can collapse all of that into a single matrix multiply and one addition of a bias vector. And so what that says is without the activation functions, neural networks are just linear functions of their inputs. So this activation function is really important. And what it does is it introduces nonlinearity into that function and allows us to model these really arbitrary, complicated functions. So for example, if we're trying to do classification here, or draw in 2D, we want to draw like a decision boundary between these green points and the red points. If we didn't have activation functions, the network would only be able to learn a linear separation. And that doesn't work when our data is drawn from these much more complicated spaces or kind of manifolds. And a neural network is with the activation functions is able to draw much better decision boundaries on this type of data. Okay, so let's go back to that task I was just showed before, which was trying to classify images. So let's try and think about in more detail how we would do this using a multi-layer perceptron. So suppose we have an image of a dog, and we want to output the probability that it's a dog or not. So maybe we have a probability that it's a dog or probability that it's a cat, for example. So we have two outputs. So what's the number of inputs that we have? So to be able to feed this to a multi-layer perceptron, we need to, as I said before, we need to take that image and flatten it into just a single vector. We might just take each row of the image and just stack them into the vector. So suppose we have an image which is 128 by 128 pixels, like that's a fairly small image, and we flatten that, then all of a sudden we have 16,000 elements in our vector. Okay, so the first layer of our MLP is going to have 16,000 units. So then we think, okay, so how many hidden units should we have for the next layer? Okay, well, maybe we'll try and reduce that image down to a few key values. So let's go from 16,000 to 10 to 100 hidden units. So then what does the weight matrix need to be? Well, remember each of these neurons are fully connected with the previous ones. So we have 100 neurons times by 16,000. So that weight matrix has over 1.6 million parameters in it. So that's a big jump going from simple polynomial regression with like 5 parameters to millions of parameters. So you can see that MLPs, even though they are powerful in that they have this universal approximation, they're not always suitable for certain types of inputs and outputs, and particularly when we're dealing with images. So I want to introduce the next architecture, which is a convolutional neural network. And so this came about because we realized MLPs are not great for doing these kind of image-related tasks. And there are other things to note about images that we really want to take advantage of. And the first is images that have a lot of spatial correlations in them. You know, so the color of the dog here is related to the color of the dog like further down its body. And so what convolutional networks do is we have our input again. We don't flatten it this time. We keep it as a 2D image. And we say we arrange our neurons in the next layer to be at the same locations as those pixels in the image. So it's essentially another image in the second layer. And what we say is instead of each neuron being fully connected to every single pixel of this image, we're just going to connect it to its neighboring values. So maybe just the neighboring values of the pixel here. And then we're going to use the same kind of equation to get what the output of this hidden unit is. So we're going to take these weights, we're going to multiply the inputs with the weights and add a bias vector. And we're going to do that for every single pixel in the output layer. But the key thing is, each neuron here is going to share the same weights. So we're not going to use different weights for each hidden unit. And so if you do that mathematically, that actually just turns out to be a cross correlation or a convolution. They're basically the same. You just kind of flip the kernel of the convolution operator. And so this little animation here is showing you what we're doing. We're going to scan across the input, and we're going to take the neighboring values of a pixel and sum them together as our neuron. And so the mathematical equation looks very similar. We're just replacing these multiplies with cross correlations. And what does that look like? What does each cross correlation look like? So we're going to take, for each pixel of the output image, we're going to scan across its neighboring values of the input image, and we're going to times them by these weight values here. And the size of that weight matrix just tells us what the shape of that convolutional filter is. So for example, here I'm showing a 3x3 convolutional filter. Well, we could make that bigger if we wanted. If we wanted the neuron to see a wider field of view of the input, we could have it to be 5x5 or 7x7 or whatever you like. And so let's work out how many parameters this layer would have. So the weight matrix, if it's 3x3 filter, is just going to have 9 parameters. And then that weight matrix is shared across all the hidden units of the output image. So we only have 9 parameters compared to like 1.6 million. And so this is way smaller than an MLP. Another kind of thing which is interesting, because these weight values are shared, you can kind of easily see that if I shift my input image slightly to the left or to the right, the output of this layer is also going to get shifted, and it's going to be the same output, it's just going to be shifted left or right. And so we call that property kind of translational equivariance. So this is like a bias that we've encoded into our model, like a property of the CNN that we assume is true about the world and of the functions that we're going to train it to represent. And so this is an example of, we call these inductive biases of our neural network. And this is really important to understand, is that neural networks are not equal in that some neural networks approximate certain functions better or compared to other neural networks. Okay, so in practice, we actually extend convolutional neural networks in one way, and that is we extend it to have multiple input channels. So actually, if you take an image, usually these images are actually composed of 3 channels, so like a red, a green, and a blue channel. And so the way you can think of that is we just have 3 images stacked together that we're going to input to the network. And we can also have multiple channels in our output layer as well. So instead of just 1 image here, we have three, for example. And so then how does the CNN work in this case? Well, it's exactly the same idea. If you take a single hidden unit of the output here, well, instead of it just being connected to the first channel, we also have connections to all the other channels too. We just times them by the weights, add a bias, same as we did before. And so what that does, if you write down the convolutional layer definition, we're just adding an extra sum here across the different channels of the input. And what we have to do is we have to make this weight matrix. Well, now it's not really a matrix, now it's a tensor. So this is a tensor with 4 different dimensions in it. And the extra 2 dimensions tell you, account for the channel of the output layer. So the channel that the hidden unit is coming from, and the summation over the channels of the input layer. So then our weight matrix has shape 3x3, for example, and then times by the number of input channels and the number of output channels. So say, for example, we have 3 input channels and 3 output channels. Then C in, C out is going to be 3. So then we have 3 times 3 times 3 times 3, which is 81 parameters in our layer. And this is great because this allows each kind of channel to learn maybe a separate feature of the inputs. So for example, this first channel might learn like edges in the input, and maybe the second would learn like different colors, for example. And we can extend CNNs in other ways too. So for example, we can have 1D CNNs, so convolutions on 1D inputs instead of 2D inputs, and 3D CNNs. In fact, we can have ND CNNs if we want. Another thing you can do, you can start to play around with the filter itself, and instead of having connections to the neighbors, you could have connections to every other neighbor, and so we call that a dilation. And we can also have strides as well, so we can reduce the size of the output image here by striding every 2 pixels instead of every 1 pixel. So yeah, there are many different kind of extensions of CNNs that you can do. Okay, so what we find is when you compose these layers together, I showed just a single layer there, but in practice, what we're going to do is we're going to feed we're going to have many layers composed together. And what you start to see if you train these CNNs on like image classification tasks or image generation tasks, we see that the layers start to learn hierarchical features. So for example, if you train a CNN to like generate images of faces, what you see, if you look at the outputs of the first layer, you can see it generates very simple features of that image, so like lines basically, and kind of colors. And the second layer will kind of compose those features together into like small parts of the output. So for example, if you're generating faces, it will create eyes and noses. And then the final layer composes all these together to form like your output. And this is a really important idea, really, is of learning features of your inputs, and not just features, but hierarchical features. And this kind of representational power, the ability of deep neural networks to learn their own features of their inputs, is really powerful. And so if you look empirically, we see by increasing the depth of the network, we generally get much higher performance. And this is kind of a trend over the decade of machine learning. We've started with small numbers of layers, and we've gradually increased them. So the neural networks today are using like hundreds of layers to train. So for example, you can plot here a convolutional network here with 3 layers. And you can compare it to the same network with 11 layers. And we see that this is trained on classification of digits from Street View imagery. When the authors created this plot, they tried to make it fair in that they tried to keep the number of parameters in the neural network the same for the 3-layered CNN and the 11-layered CNN. So it's not about increasing the number of parameters to improve the accuracy. It's about adding layers, making your CNN deeper. And perhaps it's because of this kind of hierarchical representation that they learn is the reason why their performance improves. So remember I was talking about like inductive biases of neural network. The CNN has a translational equivariance. Well, a deep neural network has this kind of bias, or it encodes this very general belief that our function is composed of lots of simpler functions. So it's kind of like how a program would work. If you write like an algorithm on a computer, we start with like a single input, and we build that input with many different operations. And it's kind of the same with a neural network. So many people like to compare like neural networks as like learning programs, and that's kind of how you could think of it. Yeah.
Why is the lower blue line where we have only 3 layers, why is there like a maximum up to which the accuracy goes down again?
Yeah, that's really interesting. I'm not sure, to be honest. This is something that there are many reasons why there are many things that affect the accuracy of neural networks. And actually, next lecture we're going to talk a lot about all those different reasons. And so you can have like approximation error, you can have like error from the optimization process, etc. So yeah, I don't have a good answer. Okay, so I've given you what I think is the most basic concept of how deep neural networks work. So now I want to talk about some of the popular tasks that we use deep learning for. So I'm not going to talk about scientific tasks now. For now, I'm just going to talk about kind of more computer science tasks that deep learning is traditionally applied to. So typically people kind of break these down into two buckets, supervised learning and unsupervised learning. I understand the reasons why we would call it that way, but I think my preferred way of thinking about deep learning is still this statement that I want you to take away with is in all of these cases, we're still fitting a neural network to some data. So it's just function fitting to data. And we are even doing that in unsupervised learning. It's just the way we call the outputs and the inputs of the network. We call them, we do it in a slightly different way to how we do supervised learning. So I'm going to talk you through some specific tasks in these. So for example, regression, classification, and then some unsupervised learning techniques as well. Okay, so let's start with probably the simplest. So this is regression, and this is exactly the example that I've been showing you to motivate the rest of the lecture. Yeah, this is basically, I have some underlying function. It's a continuous function. And I have some points on that function, and I want to try and fit a function to it. And typically we use like a mean squared error, as I've been showing before, as our loss function. And the neural network is simply directly approximating that function. So it has the same inputs and outputs as that function. Remember, as I said before, X in general is a vector with dimensionality n, and Y is another vector of dimensionality n. Okay, so I mentioned before, to create this data, I sampled from the polynomial, but then I added some Gaussian noise to it as well. And then all of a sudden, it's actually a better way to think about this problem is to use probability theory, especially if your outputs are like random variables, like they can have some randomness to them. And actually, a lot of tasks that we want to study, you can frame it as like as a probabilistic task. So how would we? So I'm quickly going to show you a kind of probabilistic perspective on regression. And so what we say now is y is like a random variable, and it's drawn from it depends on x, and we have this unknown distribution, which is the probability of y given x. So it's a conditional probability distribution. And what we'd really like to do, instead of just learning like the value of y, we'd actually like to learn the distribution of y given a value of x. So like, what are all the possible values that y could take? And so what we're going to say is, okay, we're going to learn a probability distribution instead of a single function. And just as we did before, that probability distribution is going to have some extra variables, theta, which probably don't relate to anything physical in the real world. But nonetheless, they're variables that we assume exist. And we're going to try and figure out what the values of theta are that give us a good approximation to the true conditional distribution. Okay, so to study this further, we need to make a bunch of assumptions. So the first is, okay, well, let's just assume that this is a normal distribution. And that is exactly what I did actually to generate this data, right? I sampled each point from a normal distribution and added that to the polynomial. So we can say, okay, here's my distribution here. It's going to be a normal distribution, and the mean of the distribution is just going to be the output of the neural network. So the neural network here is giving me the mean of our distribution. And for simplicity, I'm just going to say my standard deviation or variance of that distribution is going to be 1. Okay, then what we need to do is we need to use some like statistical techniques to estimate what theta is. And there are many different ways to kind of estimate theta. One of the most popular methods is called maximum likelihood estimation. And what we do is we say, okay, theta, the best value of theta is the one that maximizes the probability of our training data given the value of theta. So that kind of makes sense. Like we want our data, the training data, to be probable. We don't want it to be improbable given our model of the data. And so you can you can express the probabilities of the data here. This is just our individual training points here, given the value of theta as this thing. And so what we assume here is that each data point that we see, each training data point, is independently and identically sampled from this Gaussian distribution. So we're saying none of these points are like drawn with any don't depend on the value of the points before them, so they're independently sampled. And so if you make that assumption, then this probability of all the data is just the product of all those individual probabilities together. So this is just a product of these Gaussian distributions. Okay, so that's what we have here, this product across all of our training points here. And so then how do we maximize this data likelihood? Well, if you look at this closely enough, it's fairly easy. You can take logarithms of this function, and that just turns this into a sum and gets rid of the exponential. And then you end up with a minimization instead of a maximization, because we have a minus sign here of exactly the mean squared error. So you can see maximum likelihood estimation using a normal distribution is the same as if we were just training with our standard mean squared error loss function. So it's just a really nice way to kind of bring the two theories together. But remember, this is making a bunch of assumptions, like specifically that our data is normally distributed. And so this task in general of learning the probability distribution is actually really hard. Okay, so classification. This is the next kind of supervised learning task. And so the idea here is, yeah, given an input, we want to classify it into different classes. So for example, an image of a dog, and we want to say, is it a dog or is it a cat? And so what we want to do here, again, we have to use kind of probability theory to really understand this problem. And we say, okay, we want to learn this distribution here. It's given a value of x, which is this image of a dog. What's the probability that y is either a dog or a cat? And so before we were talking about a continuous probability distribution. Here we have a discrete probability distribution, and that's because y can only take two values, like a dog or a cat. So we use these capital P's instead of the small p's. Okay, so we can use the same technique to train the neural network as we did for regression. So we're going to use maximum likelihood estimation to estimate what the values of theta are in this approximate probability model that we're going to try and fit to the true conditional distribution. So how do we do this? So one way to write it is to say, okay, we have two potential outputs. We have a dog or a cat, and we're just going to encode it as a vector and we call these one-hot vectors. So this is a vector here that has a 1 in the class, the true class of the output. So this vector here has 4 elements. So this would be for an output that has 4 classes, for example. So given this value, this is the kind of encoding of the output here. We can say that our approximate probability distribution is the neural network raised to the power of the element of y multiplied by all the outputs of the network. So what's actually going on there? So basically, we're saying each output of the neural network represents the probability of each class. And so if we times those outputs together, but raise it to the power of whatever the 0, 1 here is, we're essentially just extracting the probability of that individual class. It's just a kind of mathematical expression that makes it easier to write down the data likelihood here. But the most important thing to understand is that we need to make sure that the output is a probability distribution. And so the thing that we need to make sure is that these output probabilities sum to 1. So specifically this property, like summation over the different classes equals 1 for the neural network. Okay, so this is the probability of y given x. And so we have lots of examples of y and x. And so again, if we assume that each of those examples is independently and identically distributed, we can just times our probabilities together of the probability of the entire training data set. So this is what our data likelihood looks like. And then we use maximum likelihood estimation. What is the value of theta that maximizes the probability of our training data? And so it's just this product with this single probability distribution here. And again, you can take logarithms of this, and you end up with this expression of our loss function. And this is known if you look at it, in PyTorch or TensorFlow. This is the cross entropy loss. And it measures the difference in kind of entropy between the neural network's probability distribution and the true distribution of training points. So there's one other thing we have to make sure. Like I said, we have to make sure that the outputs of the neural network sum to 1. And so what we do typically is we use this thing called a softmax output layer. And so we take the final outputs of the network, which I'm calling Z here. And we just use this expression, we exponentiate Z and divide it by the sum. And so it's normalizing. If you sum across all the different elements of the output, you would get 1. And so that's how we would frame kind of classification using deep learning. Okay, so let's now move on to unsupervised learning. So everything I showed before, we call it supervised learning because we have examples of inputs and outputs of the network. So we say inputs and outputs, or maybe labels is another way we would describe it. Unsupervised learning is a setting where you only have kind of inputs. So you just have an example of one thing. So for example, you could have many examples of images of dogs, for example. So then you say, well, how can I even do learning if I don't have any examples of outputs of the network? So then you have to say, okay, I'm going to learn something about the structure of X itself, the input of the model. So there are many things you can do. You can try and learn about the structure of X. One of them is to try and learn kind of really whether you can condense your input into a set of really salient features. So for example, here, you may be able to condense this image. If you think about kind of image compression algorithms, when you have blocks of areas which are the same color, you can just say, okay, this is just a single value, which is the color of that entire area. And then you've reduced the number of the amount of elements in that are needed to describe that image. And so this is one example of unsupervised learning is, can we compress this image into a set of kind of latent variables, which have a much smaller dimensionality than the input itself. So yeah, this is exactly the task. Given a set of examples here, find some features, so a function of X, which are like salient descriptors of X, so like important features. And the key point is X here is has n elements, and Z, the latent variables, has d elements, and we would choose d to be much, much less than n, so like a compression task. So how would we learn this? Well, one way is to use like a convolutional network, especially if we're dealing with images. So we would take an image as input and pass it through a bunch of convolutional layers, and they would slowly reduce the size of that image, for example, by using strides, as I was talking about before. Reduce the slice down to a single vector with like maybe 5 or 10 parameters in. Then you would use the opposite operation. So you would use more dense convolutional networks, what we would say is transposed convolutions, to expand that back out to an output that has the same dimensionality as the input. So basically another image. And then you can train this whole thing by just having a loss function which tries to get the output of the network to equal its input. And by doing so, it learns something interesting in the middle. So an example of this is variational autoencoders. So these take this kind of idea, this compression model, but it frames it in a probabilistic framework as well. And so, for example, if you train this on images of digits, so this is the MNIST data set, kind of a classic data set in machine learning, and you just have 2 values in the latent space here. What you can do is you can then sample those values, so you can scan them across their range and see what the output of the network would be, and you can see what each latent variable is sensitive to after it's been trained. And so you can see here that these two variables like map between all the numbers. So you can identify every single number in here, and they have like a nice smooth interpolation between the numbers. So we're transforming our input into some other space using a very nonlinear function or kind of transform to get what that kind of salient variables are in the inputs. And so if you think about in science, we want to do things like equation discovery or learn kind of fundamental factors of variation about the world. This is a potentially very powerful way of doing it. And we'll show you examples of kind of feature extraction for physics. Okay, another task is autoregression. So again, all we have is a bunch of examples of inputs of neural networks. And so one example might be we have the share price of many different companies. Or another example might be we have like lots of sentences, for example. And so the whole point of autoregression is given some past values of those examples, can I predict future values? And that's the general concept of autoregression. So for example, like given all the share price up until 2020, can I predict it today? Or if I have this sequence of words, can I predict what the next word is in that sentence? So this is basically how ChatGPT works, as I was talking about before. And again, there are many different machine learning models that you can choose to do this type of modeling. So one model that is very popular are these kind of what we would call recursive neural networks. And so the idea is that you take your input, you take one value of your input here, you transform it to some hidden vector h using maybe a convolutional layer or whatever type of layer you want, and then you repeat that operation, feeding in new inputs until you end up with some kind of a hidden state of the network, and then you start predicting outputs. So this is kind of what we would call this an encoder and a decoder sort of architecture. There are many other ways to do this as well, but this is just one example architecture you could use. Okay, and then the final kind of unsupervised learning task, which is very popular, is what is called generative modeling. So this is maybe a slightly different task. This is saying, okay, I've got a bunch of training data here, and these are just images of celebrities in this case. And so given this training data, can I learn to generate a new image of a celebrity or a face? And so if we were going to talk about that mathematically, we would say, given many examples here, sample from some probability distribution, P of X, can I learn to sample from P of X? And it turns out you can train neural networks to do this very, very well. And a very, very popular model for doing this is called GANs, so generative adversarial networks. I'm not going to go into detail about how GANs are trained, but the kind of high level way that they work is, well, the high level way that you train it is you have this generator here, which is this model here. It's usually a convolutional network that takes like a random number as input or a bunch of random numbers and outputs a generated image. And the way that you train it is you have another network called a discriminator, and that says, given that generated image of the generator and a true image that we have in our training data set, can you tell me what the difference between those two images are? Like which one is from the generator and which one's real? And by doing that, you can train both of them in this kind of competitive way. So it's like a zero-sum game somehow. Yeah, this makes the discriminator better, but also the generator learns to produce more realistic images, and then the two kind of compete in their training loss. Okay, so we'll take a little break and then we'll get back to it. Yep.
Mit dem Projekt, ich war letzte Woche nicht hier.
Sorry, I was speaking.
Oh, sorry. How does it work with the project? I was here last week.
Yeah.
Is there a state when we will be given them? Or?
Yeah. So I showed a slide at the start.
Yeah.
So I definitely have a look on that in Moodle.
Okay. Yeah.
But briefly, I'm going to give you the projects late April.
Yeah.
And it's going to be like 3 or 4 tasks.
Okay. Yeah.
You'll have maybe 5 to 6 weeks to work on.
Okay. Yeah.
And yeah, we'll talk about, we'll introduce the tasks in a tutorial.
Oh, okay, great. Okay, that's all right. Okay, yeah. So I didn't miss anything.
No, it's fine.
Thanks very much.
Okay, everyone, if you can take your seats. Okay, let's get started. Okay. So here's the overview of the lecture again. So I started by telling you like the fundamental concepts behind deep learning and neural networks. And then I showed you some of the kind of key tasks that we typically use deep learning for. So now what we're going to do is we're going to get more into how we actually train these neural networks. And I was saying that fully connected neural network has like 1.6 million parameters. And if you think of like a model like ChatGPT, for example, it has billions of parameters. So this is actually not trivial at all to be able to like optimize those parameters and do it in an efficient way in an algorithm that actually runs quickly. And this is like really important. And kind of these advances in training neural networks over the last couple of decades has really made them powerful. And these this is what I would call like these advances in training schemes that have improved neural networks. So I'm going to talk about gradient descent, and then I'm going to talk about algorithms that we use to do gradient descent efficiently. And this is backpropagation, and more generally, this is something called autodifferentiation. And autodiff in particular is something that we're going to rely on very heavily in the rest of the course. And so it's really important to like understand how this works. And if I get time, probably not. If I do, I'll show you the live coding. Okay, so how do we train neural networks? I've already said the most common algorithm is gradient descent. And as I said before, our neural network approximates y. If we're doing regression, we just have a least squares loss function. And then gradient descent takes this loss function and takes the gradients of that loss function with respect to our parameters, and then descends, starts with an initial guess of the parameter here, and descends in the gradient direction using some step size here to update the parameters. And we run this gradient update step like thousands or even tens of thousands of times to train neural networks. So theta here, we have many values of theta. So these could be like millions of parameters. And so we need to estimate the partial derivative of the loss function with respect to each parameter to update each parameter individually. So we just combine this thing together and we call this the loss function here. Okay, so how do we actually evaluate that gradient? And so what we can do is we make use of the chain rule. So as I said before, these neural networks are simply just function compositions. So we just take a function and we compose it with many other functions. So each function here is like a layer of the neural network. So for example, our fully connected network, we have H and then G. So H is just the first layer here, the weights times by X. G would be passing it through the activation and then doing the same operation again. And then we just compose these over and over again. And so how do we evaluate the derivative of a set of composed functions? It's just the chain rule. This is like differentiation 101. The slight kind of subtlety here, or what makes it more complicated, is these functions are not scalar functions, but they're vector value functions of vector inputs, right? So then we have to start thinking about these types of functions and how we apply chain rules to these functions. Well, it's the same idea. We just have to use the multivariate chain rule. So if we have the network, if we want to say, learn the derivative of the network with respect to the first set of weights, this in general is a vector, and this is in general, you can think of the weights as a flattened vector. So this is this derivative here, we actually want to figure out what the Jacobian is. And so the Jacobian here is just a matrix which has the elements of F along the rows and the elements of G along the, the elements of F along the columns and the elements of G along the rows. And we want to evaluate what J is. And the multivariate chain rule says, okay, if I have a function of these composed vector value functions, I can just apply the chain rule here, and each of these is a matrix, a Jacobian matrix, dH by d omega, dH by dW, dG by dH. Each of these is a Jacobian, and we just do a matrix multiplication of those Jacobians to get the final one. And so you can show that this is true. Okay, so here is our loss function. Here we have the difference of the network's output and y squared. So we can already do one step of the chain rule. We can differentiate this thing just basically like x minus a single value. And so then we can turn it into this, which is 2 times the network minus the training example times by the derivative of the network itself with respect to whatever with respect to the parameter. Okay. So then we can start applying the chain rule further and further down into the network. And so, yeah, I said before, the neural network, we're going to think about just the fully connected network here. It's composed of F, G, and H. So we can write F as this, G as this, H as this. And then we can, it's fairly simple to show actually that the Jacobian here, dF by dG, is simply my weight matrix times by a diagonal matrix where its elements along the diagonal are just the derivative of our activation function. So remember, the activation function is just an element-wise operation. So that's what gives me a diagonal matrix. So you could do that for F and G. Then what we want, instead of th by dx, we actually want dh by w1 because we want to figure out what the derivative of the network is with respect to the first set of weights. So I'm gonna come on to how we compute this in a minute, but we'll just leave it as a derivative for now. And so this is our expression for the derivative of the network with respect to w1. And so each of these, as I said before, these are just matrix multiplies. So this is a matrix, this is a diagonal matrix, etc., etc. Okay, so what we need to think about is dimensionality. I've said all of these are matrices, but what are their shapes and sizes? And it's really important to understand what these are. So we need to understand that, we need to think about what the architecture is itself. So let's just assume that the output of the network is one element, so it's a scalar output. Our hidden layers have 100 elements, so 100 hidden units in each layer. And then X, let's say it's that image of the dog before, so it's 128 by 128 image. But because we're feeding it into a fully connected network, we're just going to flatten it into a single vector. And so then the input layer just has 16,000 units. Okay, so we already worked out before the first set of weights is going to be the number of hidden units times by the number of input units, which is 100 by 1.6 million. 100 by 1.6 million. Okay, so then if we think about the chain rule again, H here is a 100 element vector, and W is that 100 by 1.6 million. So the Jacobian here is a matrix which has 100 rows and 100 by 1.6 million columns, or the other way around. So you can see here, this box here is dH by dW, and it's 100 by 1.6 million. So that is an absolutely huge matrix. It has 160 million elements, or if you put that into computational memory using like 4 byte elements, that's nearly a gigabyte's worth of data in a single matrix. So that's really difficult if we want to train the network, if we have to evaluate that entire matrix. Not only do we have to form that matrix, but we have to do all these matrix multipliers as well. So the Jacobian G and H, this is 100, G is 100, H is 100 element vector. So the Jacobian is 100 by 100. And then the output here, df by dg, we've got a scalar output of the network. So then that's just a vector. So we have to do all these matrix multipliers to get our final update here, which is the gradient of the weights. So we know the W1 has 1.6 million elements. Okay, so let's think about the number of operations required to evaluate the right-hand side of that equation. So first of all, we're going to think about evaluating that from right to left. So what do I mean? We're going to take this matrix first, and we're going to multiply it by this matrix, and then we're going to take the output of that and multiply it by this vector to get this. So that basically means doing 100. So this one times this one is 100 by 100 times by 100 by 1.6 million, which results in a 100 by 1.6. And then we do the vector 1 by 100 and 100 by 1.6 gives us our final weight matrix. So this is a lot of computation because we have to do one massive matrix multiply in the middle here. So alternatively, what we can do is we can evaluate that expression in reverse. So we can say, okay, we're actually going to evaluate this big matrix, this multiplication sequence from the left to the right. So then, and it will give us the same output, right? It's just multiplication. But in this case, we start with 1 by 100. This is very small, times by 100 by 100, relatively small. Gives us a 1 by 100 matrix. And then we do this one, which is a larger matrix multiply, but still not as large as the first one that we did in the right to left version. So you can see here, this requires much less computation because we just have vector matrix multipliers instead of a matrix multiplier. So this is a real key takeaway when you're training neural networks like this is, the order matters when we're doing the chain rule and gradient descent. And so we would call the right-hand side here reverse mode differentiation, and we would call the left side here forward mode differentiation, based on how we evaluate the chain rule. And so what you find is if you have loss functions, like scalar outputs to the network or scalar loss functions with lots of free parameters, the Jacobian of that loss function is very wide. So it's like a single row and lots of columns. And typically this reverse mode differentiation is way, way more efficient for evaluating that type of Jacobian. On the flip side, if you want to evaluate Jacobians that are very tall, an output that has many values, then you would use the forward mode differentiation. Okay, so that's pretty good, but we still have one problem, which is this last matrix multiply here. We still have a matrix here, this dH by dW1 here, this Jacobian here. It's still 100 by 1.6 million, so this is still a gigabyte in size. Okay, so then we need to get to what does it actually look like as a matrix? And so this is this derivative that I was talking about before. What is dH by dW? Well, it's just H is W1 times X plus B. And if you actually evaluate that each individual element of that matrix, well, it's very simple. It's just a linear thing. So the elements of the matrix are X, X1, X2, X3, like the elements of X. And those elements are just like duplicated across, chunked across the rows of the Jacobian. And the Jacobian across these elements here is 0 everywhere. And so then if you think about that last matrix multiply, which is dF by dH, which is just a vector, and this Jacobian here, it turns out the resulting vector that you get is just this thing. And if you stare at that long enough, you can see that is just the outer product of two vectors. So one that contains your values of X here, and another that contains the values of the hidden or the derivatives coming from the chain rule. So another key takeaway here is even though we have these massive Jacobian matrices, we don't actually need to populate them when we're doing gradient descent. And what we actually only need to specify is the vector Jacobian product of each layer of the network, or each fundamental operation that we do. So yeah, we can get rid of this big matrix multiply here and just turn it into a very simple outer product. And you can see there that we've gone from like really massive computation to a very efficient training code for getting our derivatives of our network. And this is the key point that allows us to kind of train billions of parameters, is to exploit these vector Jacobian products and using reverse mode differentiation. So cool. So yeah, this is another takeaway. Essentially, training neural networks computationally just comes down to a bunch of matrix multiplies. And that's true across pretty much every architecture. Essentially, it's just matrix operations. And another really cool thing is GPUs perfect for these types of parallelizable computations. So a matrix multiply can be done in parallel for each element of the output matrix. And so GPUs with their thousands of cores can carry out that way quicker than a CPU. And so what you would find if you run deep learning on GPUs, you usually get 10x to 100x speedups compared to CPUs. Cool. So this algorithm specifically applied to deep learning is called backpropagation. Yeah, so how do we do it in practice? So what we do is we do two passes. The first is the forward pass, where we just run the network forward and we get the outputs of all the layers. And then the second is what we call the backwards pass. And we just save the outputs of these layers here, and we plug that into our chain rule. So these are the Jacobians that I just showed before. And we have fast ways of computing the vector Jacobian products instead of having the full Jacobians. So for example, this outer product. Yeah, and so you evaluate the chain rule. It's really important to evaluate this from left to right to make sure you're not doing too much computation. And then that kind of other things is, okay, well, we also have this summation in the loss function over all of our training examples. So we need to do this operation across every training example. And so that just turns into a batch matrix multiply. You're just batching a lot of matrix multiplies together. And GPUs have very fast code implementations of batch matrix multiply. And also, I've just shown this for the single weight matrix, but you can see how this equation is very similar for the other weight matrices in the bias vectors as well. Okay, so that sounds pretty complicated. But the great thing is we don't actually have to worry about this when we're doing this in practice using modern deep learning frameworks. So PyTorch, TensorFlow, JAX, all these different software environments, the core reason why they're so useful is because they take care of this differentiation for you. And so what you just have to do when you're writing in these languages is define the forward pass, and it will use this thing called autodifferentiation, doing this reverse mode, forward mode differentiation for you without you having to worry about all the fundamental operations. Okay, so I showed that for a fully connected network, but autodifferentiation just takes that and generalizes that idea to an arbitrary program. And so what do I mean by an arbitrary program? I mean an arbitrary composition of functions that we apply the chain rule to get the gradients of the output with respect to the input. So how would you actually code this, or code like an autodifferentiation engine? So what is useful to do is to think about your function here as a graph. And so as a directed graph. And so you have kind of the inputs to the function here, x, w1, b1, w2, b2, for example. They're leaves of the graph. And then the intermediate layers, the hidden layers, and the output, the loss function, is computed from the leaves of the graph. And so if we want to get the derivative of L with respect to W1, for example, we apply the chain rule backwards through this graph. And so for each operation, like each node of the graph here, we need to define what that primitive operation is. So that could be like a sum or an activation function, for example. And we need to define how the forward operation works and how these vector Jacobian products work, or the Jacobian vector if we're doing forward mode differentiation. So if we define the graph in these three things, then evaluating the chain rule or just doing auto-differentiation in general, you can think of it as message passing between this graph. So we start with an initial vector, if we just have a scalar loss function, that's just going to be the value 1. And then we take that and then we apply the chain rule based on the vector Jacobian products of each operation on the graph. And we propagate these messages backwards through the graph. And so you can see how we can kind of make this general for any type of composed function, and it doesn't just have to be a fully connected network. You can also do this for for loops as well in Python. So you can just unroll your for loop and that just turns into one big graph. So then you can start coding like recursive neural networks, for example. Yeah, so I mean, if any of you have used PyTorch before and we had the tutorial, you probably used this thing called loss.backwards. And this is the thing that created, evaluated the gradients of the network to use it in gradient descent. So if you actually look at the description of what loss.backwards does, is exactly what I'm describing. So, you know, you have a graph with graph leaves here, and it's evaluating the chain rule, and it's doing the Jacobian vector product of your loss function. Okay. So some people get confused about what autodiff is. So it's important to think about what it's not. So autodifferentiation is not symbolic differentiation. So we're not, when we're doing a scheme, we're not coming up with like a mathematical equation that says dy by dx equals this expression. It's also not doing an approximate gradient. It's not doing like finite differences, for example. It's giving you the exact gradient evaluated using the train rule of your function. And so, yeah, it's primarily a way to efficiently compute gradients of arbitrary functions. And that's how you should think of it. Okay, so I do have 10 minutes left, so I'm going to try and do this demo. So for those of you online, I'm just going to share a different screen for you. Okay, so what you're seeing here is a Jupyter notebook. Can you see the text okay, or is that too small for you? Is that too small? Yeah, okay. Okay. Right, okay, so what I'm going to try and do is implement that backpropagation algorithm just using NumPy in Python. So I'm not using PyTorch or TensorFlow or anything like that. It's NumPy is just a basic math and array operation library in Python. And so first of all, we're just going to import these libraries, and then we're going to generate some training data. And so the training data that I'm using is just this function that I've been showing throughout the lecture, and it's just this polynomial with these noisy points. And so what we're going to try and do is fit this neural network that I've just shown in the lecture to this data. So again, we have composed of functions, and we have our first hidden layer, second hidden layer, and the output of the network. And then we have this equation. We're using the chain rule to get our derivative, our loss function with respect to the weights. And it was just this expression here. So the summation over all of our training points times by these analytical expressions for your Jacobians. And reverse mode, we have to make sure we evaluate from the left-hand side across to the right-hand side. Okay, so first thing we'll just do is print the shape of my inputs and my outputs in the network. So this is my training data that I'm going to use. So you can see I've got each thing here is a tensor with 3 dimensions, and the first dimension is the number of examples, the number of training examples. So we're going to evaluate this expression using batch matrix multiplies. So we need to have the number of examples as our first dimension in our tensor. And then X and Y, I'm phrasing them as matrices, but they're just 1 by 1. So they're just basically scalar values. Cool. And then the next thing we do is just define what our activation functions are. So we're just going to say activation is just tan h. And remember, we also need to know what the derivative of the activation function is to evaluate our chain rule. So the derivative of tan h is just 1 minus tan h squared. Cool. And then the next thing we need to do is to define our weights of the neural network, so and the biases. And so these are the things that we're going to tune or train in the network. So I'm going to assume I've got 2 hidden layers, and the first hidden layer has 8 units, and the second one has 16. So you can see the first weight matrix is taking the scalar vector to a 8 valued vector, and then we're going to go from 8 to 16, and then 16 back to 1 as the output. So the output is just going to be the single number. We're just going to sample these from like random distributions, uniform distributions. We'll get onto why we do this square root thing in next week's lecture. And so what I need to do is I need to define my forward pass. So the first thing that I want to compute is h, which is omega 1 times x times by b1. So let's go ahead and write that. Ooh. So in NumPy, we can just use this at symbol to denote a matrix multiply. And also, if your matrix has extra dimensions at the front, it just does a batch matrix multiply for you. So it already does that for me. So W1 times by X, and then we're going to add our bias vector here. So that's going to have shape in examples 8 by 1. So this is 8 hidden units because we're using this W1 here to increase the number of elements in the vector. Okay, then G is going to be, we look at our equation for G, it's W2 times by the activation of H. So we do W2 times by, and then our activation function is S here, so we just pass that to S. And then we add B2, which is our bias vector 2. And then the same thing for F. This time we're not going to use activation for the final output of the network, but it looks the same as G. So we just pass this through G like this, plus B3. Cool, so that's done the forward pass. And remember, as I said before, we have to collect these values of H, G, and F so that we can evaluate the gradient. So the first thing we want to do is evaluate DL by DF. So DL by DF here is just this first term of the loss function here. So we say DL by DF equals 2 times F minus Y. So 2 times by F minus Y, like this. So remember, Y is just our training data that we have. This is just going to be a bunch of scalar values because the output of the network is a scalar and Y is a scalar. Then we want to compute the rest of our elements of the chain rule. So DL by DG, which is simply going to be this term here. So W3 diag times by this. So we do W3. Again, this is a matrix multiply. And so there's this expression here that you can just use to get a diagonal matrix in NumPy. And we're going to times that by the derivative of our activation function. So that's ds as a function of G here, like this. So what we want to make sure here is that we're doing reverse mode differentiation. So we want to make sure we evaluate this expression from the left to the right. That's the most important thing. So we're going to make sure that this is all in brackets. Yeah. Well, yeah. I mean, we're just evaluating a single thing, so that's fine. And then DL by DH is just, again, this weight matrix thing here. So we're just going to copy this. It's the same operation, but we're passing in H here instead of G. H, and then we want to make sure that this is 8 instead of 16 because of the dimensionality of the hidden units. So so the final thing I need to do to get derivative of L with respect to G. So this is the derivative of L with respect to G here. Is I need to times this thing that I've computed here, this W by diag by DL by DF. This is just evaluating the chain rule. So I need to times this by DL by DF, like this. And so this is what I meant by I got that slightly wrong. So this is what I meant by evaluating the chain rule from left to right. We want to make sure that we evaluate this thing before we evaluate this second matrix multiply. So that's what it should look like. And then the same thing here, we just start applying the chain rule to the next part. So dl by dg times by our weight matrix, like this. And you can see how we're evaluating this left to right. And I'll put this in brackets. Like this. Cool, so that should work. The rest of the code I've written to make it quicker. So we now have dl by dh, dl by dh here, but we actually want dl by dx. So then we need to define that vector Jacobian product. And we said before that was just an outer product of this whole thing times by x. And so that's just a multiplication, and we just transpose it to get the right dimensionality of the gradient of the weights. The biases are actually even easier. We don't even have to do this product. We just take the gradient itself. And then the final thing I'm doing is just as a mean over all of our training examples. So you see we're doing a mean over the first dimension of the output there. So these things should just be the derivatives of each of our weight matrices and our bias vectors. And then we can just do a simple gradient descent step. So we specify the learning rate. We usually do it quite low. We'll get into optimization next lecture. Then we take a step, and then we just run this in a big for loop over like 2,000 examples. And then the final part of the code is just going to plot the network output over every 500 steps. So yeah, see, so it starts off with like a flat function here. And then as we increase the steps, we start learning the output of the network. And you can see how simple it is to like code up backpropagation and train a neural network just in very simple Python code. And hopefully you'll get some more experience with this in the tutorials next week as well. So yeah, thank you very much. See you next week.